Chapter 3: Structure and Bonding. We know that all matter consists of tiny indivisible particles called atoms. And because there are many of them, there are equally as many elements in nature. The wonder of the chemical elements is that they combine with each other, and there's an almost infinite number of combinations that produce all the chemical compounds and stuff around us. The water we drink, obtained by combining an oxygen atom and two hydrogen atoms. The glass we drink from. The sugar in our coffee. The coffee itself. The cup and the spoon. Everything around and inside us are atoms combined. The properties of each element are defined by the atom's nucleus and by the way electrons distribute around it. These properties define the way atoms combine. Atoms react with each other through the electrons of the outermost energy layer. Atoms that have completely filled outermost energy levels are said to be stable. All other atoms tend to gain stability by having a filled outermost energy level. They can do this by either gaining extra electrons or losing the excess electrons, whichever is easier. The ions formed then combine in our first bond, the ionic bond. We know that sodium loses one electron to form a sodium ion. This electron can be transferred to a chlorine atom to form a chloride ion. So we have sodium ion with a net positive charge and a chloride ion with a net negative charge. The two ions attract each other, and this electrostatic attraction between oppositely charged ions is what we call an ionic bond. An ionic bond occurs when there is complete transfer of valence electrons from one atom to another, resulting in two ions with opposite charges. Generally, ionic bonds are formed between metals and nonmetals, resulting into an ionic compound. Consider magnesium and oxygen. A magnesium atom has two valence electrons which it can lose. Oxygen has 6 valence electrons and needs 2 extra electrons to complete an octet configuration. Magnesium transfers the 2 electrons to oxygen, and the resulting cation and anion attract each other to form an ionic compound, magnesium oxide. Sometimes, ionic bonds can involve more than 2 atoms. Consider the formation of magnesium chloride. Magnesium needs to lose 2 electrons to be stable. However, chlorine has room for only 1 electron. In this case, 2 chlorine atoms will combine with 1 magnesium atom. Magnesium atom will transfer 1 electron to each of the chlorine atoms. So we shall have 1 cation and 2 anions in this ionic bond. How do you feel about the ionic bonds? Can you draw the ionic bonding between aluminium and chlorine, and also between sodium and oxygen? Giant ionic structures. So far, we have looked at ionic compounds as single entities. Ionic compounds actually exist as large 3-dimensional structures known as giant ionic lattices. When we talk about sodium chloride, they are not individual sodium chloride molecules. Instead, the sodium and chloride ions are arranged in a regular repeating 3-dimensional pattern known as a giant ionic lattice. We know that sodium and chloride ions are electrostatically attracted to one another. Because of this, you will see that the ions are arranged so that the sodium ions are always next to the chloride ions. This arrangement is seen in all directions of the three-dimensional structure. The electrostatic attraction in a lattice structure are very strong. Each sodium ion is held in place by the electrostatic attraction of 6 neighboring chloride ions in all possible 3D directions. And similarly, each chloride ion is held in place by the electrostatic attraction of 6 sodium ions also in all possible 3D directions. Since this lattice structure is so strong, it explains some key properties of ionic compounds. Ionic compounds have very high melting points. This is because a lot of energy is required to overcome the strong electrostatic attractions holding the three-dimensional lattice structure in place. Ionic compounds are also very brittle. This means they break rather easily into small pieces. When a force is applied to the three-dimensional lattice structure, it will disrupt the regular repeating patterns of sodium and chloride ions. So the sodium ions are forced to be next to other sodium ions, and the same is seen with chloride ions. Like charges repel each other, and this repulsion essentially breaks the lattice structure. Sodium chloride, sodium fluoride, and ammonium nitrate are ionic compounds and can dissolve in water. Most ionic compounds are soluble in water. In water, an ionic compound can dissociate into its ions. So when we dissolve sodium chloride, it will dissociate into sodium and chloride ions. These ions become stabilized in water due to the polar nature of water. As you can see, the sodium ions are stabilized by the negative dipoles of water, and the chloride ions are stabilized by the positive dipoles of water. An ionic compound dissolved in water can conduct electricity. This is possible due to the presence of free-floating ions. Following on the same idea, molten ionic compounds can also conduct electricity. The lattice structure is broken at high temperatures, and so the ions become free-floating. Covalent bonds. We have seen that ionic bonds are formed between metals and non-metals because metals are eager to lose electrons and non-metals are eager to gain the electrons. What about when non-metals react? Consider 2 hydrogen atoms. Each has 1 electron and needs another one to complete the 1 energy level. But neither is willing to give up its only electron. In this case, the 2 hydrogen atoms share their electrons so that each has 2 electrons some of the time. When this happens, the shared electrons are mutually attracted to the positive nuclei all the time. This attraction between the shared electrons and the nuclei is what constitutes a covalent bond. It results in the formation of a molecule of hydrogen. The sharing of electrons can also occur between different elements. For example, a carbon atom holds 4 electrons in its outer shell and needs extra 4 electrons to achieve stability. It can do this by sharing with other atoms. If 1 carbon and 4 hydrogen atoms come together and share their electrons, carbon achieves an octet of electrons. Each hydrogen attains 2 electrons in its valence shell. This molecule is called methane. A molecule is a group of atoms of the same or different elements that are held together by strong covalent bonds. Substances consisting of molecules are called molecular substances and include most gases, water, sugar, oils, fats, sulfur, wax, and so on. A single line between the element symbols indicate a covalent bond consisting of a shared pair of electrons. 2 pairs are represented by double line and 3 pairs by 3 lines. Coordinate covalent bond. Consider the ammonia molecule we have here. In this molecule, one nitrogen atom has formed 3 covalent bonds with 3 hydrogen atoms. Nitrogen has in this case donated 3 valence electrons into the sharing deal. But still, a pair of electrons remains unused. We call this a lone pair of electrons. Now for a moment, consider an atom of hydrogen, 1 atom and 1 proton. Hydrogen has no neutrons. Hydrogen can form an ion by gaining another electron. But it's equally easy and likely for hydrogen to lose this only electron. If the second scenario happens, the hydrogen cation is simply a proton because there is no neutrons. Sometimes, this hydrogen ion can form a bond with the ammonia molecule. In this sharing, the 2 electrons are all donated by the ammonia molecule. This is a coordinate covalent bond, a special type of covalent bond in which the shared pair of electrons forming the bond is contributed by only one of the atoms. In the new molecule, the number of protons are more than that of electrons, and thus it carries a net positive charge. This is called an ammonium ion. The coordinate covalent bond is also called a dative covalent bond, and it is represented by an arrow pointing in the direction of the donor atom. Another example in which a coordinate bond exists is carbon 2 oxide. A carbon atom has 4 valence electrons and therefore needs to gain 4 electrons to fill its outermost energy level. Oxygen, on the other hand, has 6 valence electrons and needs 2 electrons to attain the stable configuration of 2,8. The oxygen atom and the carbon atom in carbon 2 oxide form 2 covalent bonds first. Oxygen then donates one of its 2 unshared pair of electrons to form a coordinate bond with the carbon atom. Since a coordinate bond is formed when the combining species share a pair of electrons, it is a type of covalent bond. Molecular structures. Most molecular substances are gases or liquids at room temperature. The atoms forming the molecules are held together by strong covalent bonds. The molecules in the solid substance are in turn held together in a regular pattern by weak van der Waals forces. The regular pattern repeats itself many times, resulting to a molecular structure. Next, hydrogen bond. A water molecule is made up of 1 oxygen and 2 hydrogen atoms arranged in a shape of a V. The hydrogens are covalently bonded to the oxygen, which means they share a pair of electrons between them. There is a principle in chemistry called electronegativity. This is the chemical property that describes the tendency of an atom to attract electrons towards itself. The more electronegative an atom is, the more it attracts electrons. In the case of water, the oxygen is more electronegative than hydrogen, and as a result, it pulls the bond electrons towards itself, and the electrons spend more time around the oxygen than they do around the hydrogen. This causes a partial negative charge to build up around the side of oxygen and a partial positive charge to build around the hydrogens. This results in what we call a polar molecule, which means the 2 ends of the molecule have opposite charges. The way the water molecules interact with each other is as a result of this polarity. The partially positive hydrogen of one molecule and the partially negative oxygen of the other molecule are attracted to each other and form a bond between them. This is called a hydrogen bond, and it is more of an intermolecular force. These bonds are weak but stronger than van der Waals forces, and thus giving water a higher boiling point. Hydrogen bonds are constantly forming and breaking. In diamond, each carbon atom is bonded to 4 other carbon atoms by covalent bonds, forming a rigid 3-dimensional structure. Diamond's density is 3.5 grams per cubic centimeters. Here, no electrons are available as they are all involved in bonding. Because of the absence of free electrons, diamond is a bad conductor of electricity. Diamond has a high melting point of 400 Kelvin or more. Graphite. In graphite, each carbon atom is bonded to 3 other carbon atoms by covalent bonds, resulting in hexagonal rings which are arranged in layers above each other. One of the carbon-carbon bonds is a double bond, and thus the valency of carbon is satisfied. Since 1 electron of each carbon atom in graphite is free to move about, graphite is a good conductor of electricity. The layers are held together by weak van der Waals forces. Due to its structure, graphite is not as hard as diamond and is greasy. It's gray in color and opaque with metallic luster. Graphite's density varies from 2 to 2.5 grams per cubic centimeters and melts at 1800 Kelvin. Silicon 4 oxide. Silicon has 4 electrons in its outermost energy level. Each silicon atom is bonded covalently to 4 oxygen atoms, forming a giant covalent structure. The metallic bonds. We have seen that metals and non-metals form ionic bonds. Because metals give out electrons and the non-metals accept the electrons. Also, non-metals form covalent bonds amongst each other because in non-metals both atoms need extra electrons and will share the electrons. What about metal atoms? They need to lose electrons, and as such, they cannot share with other metal atoms. Metal atoms will lose their valence electrons no matter what. In metallic bonding, the atoms lose their valence electrons to form ions. These ions are arranged side by side in a regular repeating pattern. The lost electrons move freely in the spaces between the metal ions. These are called delocalized electrons. The delocalized electrons act as a glue and hold the structure in place. So a metallic bond is the attraction between the positively charged nuclei and the negatively charged delocalized electrons. This is a very strong attraction and explains why metals have high melting and boiling points. A lot of heat energy is needed to overcome this attraction. This is also why metals are good conductors of heat. Delocalized electrons are also the reason why metals can conduct electricity. Metals are malleable and ductile because no matter what shape the metal takes, the delocalized electrons will conform to that shape. The strong electrostatic force will remain, and therefore the structure stays intact. So when we talk of metallic bonding, we are actually describing the electrostatic attraction between the metal ions arranged in a lattice structure and the delocalized electrons around them. Since these electrons are free to move around, the term sea of electrons is also used. So literally, the positive metal ions appear immersed in a sea of mobile electrons. And so in summary, most atoms don't exist solo. Instead, they bond with other atoms. A bond can form between atoms of the same element or atoms of different elements. You've probably imagined bonding as a tug of war. If one atom is really strong, it can pull one or more electrons off another atom. Then you end up with one negatively charged ion and one positively charged ion. And the attraction between these opposite charges is called an ionic bond. It involves complete transfer of valence electrons. Table salt, sodium chloride, is held together by ionic bonds. Every atom of sodium gives up one electron to another atom of chlorine. Ions are formed, and these ions arrange themselves in a 3D grid called a lattice, in which every sodium ion is surrounded by 6 chloride ions, and every chloride ion is surrounded by 6 sodium ions. If one atom doesn't completely overwhelm the other, they can actually share each other's electrons. This is like a mutual agreement that satisfies the need of either atom. Each atom is attracted to the shared electron in between them, and this attraction is called a covalent bond. The proteins and DNA, for example, are held together largely by these covalent bonds. Some atoms can bond covalently with just one other atom, others with many more. The number of atoms one atom can bond with depends on how its electrons are arranged. Every atom of a pure unbonded element is electrically neutral because it contains the same number of protons in the nucleus as electrons around the nucleus. And not all of these electrons are available for bonding. Only the valence electrons, the ones in the outermost energy level, only them participate in bonding. And by the way, this applies to the ionic bonding too. In sodium chloride, the electron sodium loses is the one farthest from the nucleus, and the orbital that the electron occupies in chlorine is also the outermost one. So carbon has 4 electrons available to bond, nitrogen has 3, and oxygen has 2. So carbon is likely to form 4 bonds, nitrogen 3, and oxygen 2. Hydrogen has 1 electron, so it can only form 1 bond. In some special cases, atoms can form more bonds than you would expect, but they better have a good reason to do so, or things could fall apart. Groups of atoms that share electrons with each other are called molecules. They can be small. For example, every molecule of oxygen gas is made up of just 2 oxygen atoms bonded to each other. Or they can be very, very big, like the human chromosomes containing billions of atoms covalently bonded.